All right, we are back for sections 11.4 and 11.5. So 11.4 is tests for homogeneity, or homogeneity, depending on how you pronounce it. So the chi-square test for homogeneity of proportions is used to compare proportions from two or more populations. So we're using it to compare proportions from two or more populations. So we're testing whether different populations have the same proportion of individuals with some characteristic. Okay, so the chi-squared test is still the same. It's not changing just because the context is changing. And we'll see that in this example, that our process is going to be very similar to what we've been doing. It's just that the question and answer are kind of meaning something a little bit different. Okay, so the following question was asked of a random sample of individuals in 1992, 2002, and 2008. Would you tell me if you feel being a teacher is an occupation of very great prestige? The below presents the results of the survey. Test the claim that the proportion of individuals that feel being a teacher is an occupation of very great prestige is the same for each year at the alpha equals 0.01 level of significance. Okay, so we need to run this test. So when we're doing the test for homogeneity, we're going to have our null and our alternative. Okay. And the null hypothesis is always going to be that the distributions are the same. And the alternative is the distributions are different. Okay, so status quo, right, that null hypothesis says, no, everything is the same, right, there's no change. Oops. Different. Okay, so there we have our null and alternative hypotheses. So degrees of freedom in this case. So with this one, we're going to do the number of columns. Just trying to find a space to write this. So degrees of freedom equals number of columns minus 1. Sorry, I should have put that there. Is number of columns minus 1. So in this case, that's 3 columns minus 1, which is 2. So we had 2 degrees of freedom in this one, just like we did in the last one. But now, in order to get our test statistic, we're going to need to get those expected counts, as well as our observed counts here. So let me zoom in here for a minute. Okay. So in order for us to get the expected counts, we need to get the row total, column totals, and table total for all of these. So let's do that right now. Let me just shrink this font a bit. Okay, so if we add up this row total, 418 plus 479 plus 525, it's going to give us 1,422. Okay. If we add up the row beneath it, oops. Oops, sorry about that. Let me just that better. There we go. That row total we get is 1628. Okay. Column totals. So first column over here, we're going to add up 418 with with 602. The app's being a little glitchy today. Let's see here. So we've got, for our first column, 418 plus 602. That is 1020. The next one, add those up. That actually also gives us 1020. And the last column there gives us 1010. Okay. So now using these values, we can go ahead and find our expected counts. So remember, the expected count is going to be row total times column total over table total. Okay, so if we do that for each of these, we can go ahead and make a new table here. Okay, just what do we have here? Whoops. Something like that. There we go. Okay, so row total times column total all over table total. I forgot to put the table total in here. If you add up all of these values, so you can either add these values or add these values separately, they'll give you the same answer. So in this case, we get the table total is 3050. Okay, so that's our table total for this one. So now, if we do that calculation, this is going to give us, so let me just set this up here. So this is yes and no. This is in 92, 02, and 08. Okay, and then let's get these values in here. So run that computation. The first one's going to, oops, I don't know why it's not letting me do that. There we go. So we're going to get 475.6 for the first one. I'll line these up in just a second. The second one, we also get 475.6 because, again, they share a row, and then their column totals are actually the same, and the table total is always the same. So it would make sense that those two would be the same. And then this one is 470.9. Line those up. There we go. Okay. So those are our expected counts for that first row, and then for the second row, we're going to get 544.4, and then of course these are the same row total and column total, so this one's also going to be 544.4. And then the last one is 539.1. So just line that up there. Perfect. Okay, so there's our expected values. So now we've run our computation for our test statistics. So it's observed, so 418 minus expected, so 475.6 squared over expected, 475.6, plus 479, right, observed minus expected, so 475.6 squared over 475.6. all the way to the very last one, right, which is the 485 minus 539.1 squared over 539.1. Compute this test statistic, we get approximately 24.76. So now we compare that to our critical value, so chi-squared sub alpha, which in this case, alpha is 0.01 for this test. Don't forget 2 degrees of freedom that we saw earlier. So we go into that table, find the 0.01 column, find the 2 degrees of freedom row, should be just the second row, and we find that this value is 9.210. So we always compare critical value with test statistic, right? So on our curve, our chi-square curve, so here's chi-squared sub 0.01, right, at about 9, and then our test statistic is somewhere up here, right, at about 24. So it falls within this critical region, which means that we do, in this case, get to reject the null. Okay, so if we're rejecting the null hypothesis, what are we saying? Well, we're saying that the distributions are not the same, right? That they are different among those different dates. So in other words, when they ask the question to these different groups of people over the different years, the way that people answered the question was different statistically among those different years. Okay, so this says, so there is sufficient evidence to claim the distributions are different. Okay. Alright, so again we're running that same test, and that's giving us our result here, just again looking at something slightly different than what we looked at in the last section. Okay. So now let's go to 11.5, which really short is just this page. It's just kind of summarizing what we've been talking about this chapter. So we're looking at the chi-square test statistic being used in 3 different circumstances. So we have these 3 here, of course, our goodness of fit test, our independence test, and our homogeneity test. So goodness of fit we saw last time, so to decide whether a population fits an unknown distribution, okay, if our current distribution fits another one. The independence test we saw last time, right, to determine if 2 values are independent or dependent, okay, or 2 factors, I guess. And then for the homogeneity test, decide if 2 populations have the same distribution as each other or not, if they're different. Okay, and then it gives you a nice little summary here, because the null hypothesis and alternative hypothesis for these don't change, right? In the previous chapters, we'd have to create an appropriate null and alternative hypothesis to fit the question, but in these cases, it's always just going to be the same thing for each one. So we're just going to use those and go with that. So that brings us to the end of chapter 11, to the end of our discussion on the chi-square distribution and running these 3 tests using chi-square. So that's it for today, and I will talk